you, Leslie, for this very nice introduction. So I suggest that there are some very good seats here at the front row. So these are the best seats. 3 hours sitting in those benches. Really put your back.
My second hour,
Yeah, I just sat for 10 minutes and it's already hurting my back. And I will also ask questions of people who are sitting in the back. So if you choose the front row, front rows, no questions. I will ask you questions. I will not test your knowledge.
ये वाला तो फ्रेम अच्छा रहेगा.
Okay, good afternoon to all of you. Thanks, Leslie, and the Center for Cognitive Sciences for inviting me. This is my first time at although I visit NID Ahmedabad. I also visited the Untitled campus once in 7 years. I come there quite often. Do some short courses or my colleagues there. So, just to lay some groundwork on what I'm going to talk about. So, if you have a cognitive science background, so I'm going to talk about how we designers appropriate knowledge or understanding that we have got from cognition, mostly perception, okay, and then apply it for better communication. So that's what I'm going to talk about. So, any of the cognitive science related or perception related stuff that I'm going to talk about must be quite familiar to you. But what I hope is that what I want to leave behind is how we designers or visual communicators, okay, use your field in communicating the kind of messages, stories that we want to tell. Because that's what my talk is going to be about. So, visualization is communication. Okay, so the moment you visualize anything, so I'm standing in front of you and throwing my arms around, you see my expression, I see your expression. So there is some kind of animation that is happening right here. There is a visualization. So it's all about communication. There is communication happening with visualization. So the visualization that we do is to help humans solve analytical problems quickly and accurately. So the New York Times graphics or database stories that Leslie talked about in his introduction is all about how do we tell complex or how do we communicate complex information. Sometimes it is mostly quantitative information. Okay? So information related to population, literacy rates, GDP, income levels, vote margins. So these are all very difficult for people with good literacy because the numeracy and then the analytical or quantitative literacy is not as good as our verbal literacy and our social cues and our social communication. So this is not being explored sufficiently, and the role of or the purpose of visualization, the kind of visualization I do is to solve analytical problems. So figure out, for example, what is the difference between A and B, or is A bigger than B? If A is bigger than B, by how much? Okay, so these are all the analytical problems that visualization does helps to solve. Okay? So why visualize data at all? Okay, so we are all familiar with information like this being presented on our newspapers. So this is, for example, is a typical financial section where all the stock prices are listed in the index, and people who are familiar with this, they know how to really figure out very quickly. They can quickly zoom into the area that they want because there is some kind of an organization that they are familiar with, and then they will figure out the information and therefore make meaning out of it, right? So this has been around, so people just need a little bit of education, familiarity, or some instruction on how to read things like this. Why do we need this? So you're all smart people. people here. I'm giving you two. So I'm giving you there's 12 in the first column, 12 points in the first column, and 13 points. Sorry, 12 points in the 24 points here in two columns. So these are the x and y values of those 24, each of those 24 points. Now, looking at this number, can you figure out anything? What is the relationship between x and y? It's nearly impossible to figure out. If you maybe stare at it for a little bit more longer, you might maybe realize that the difference has some kind of pattern that is being itself. And then after some time it also falls apart. So it's very difficult. But if I show you this, instantaneously it is obvious that these are all points along the circumference of a circle. So this happened in about 250 milliseconds, and then this is what you guys refer to as pre-attentive processing, right? So the goal of visualization in any case is that is to reduce any kind of a cognitive load on people to figure things out. Okay? Things can be, the people can get on with the task of what they should be doing after figuring out something, and that is what we want them to do. Okay? So the common thing is like in a new campus, I land up here and trying to figure out where to get there, and there are help available in the form of maps, direction signages, and so on, right? So that is for me to know where I should be going based on the information that I have with me. But if I'm taking too much time just to figure out where to go, I mean how to read that map, for example, or how to understand the signages, then the designer has failed in the communication, right? So that should be instantaneous. If people should not be even paying any attention, should not be investing any cognitive load on understanding that or making sense of that information. They should be getting on with doing whatever they're supposed to be doing with that information, right? So pre-attentive processing, which is subconscious accumulation of information from environment, and the best visualization to make the information you want to communicate available pre-attentively. So the best visualizations are something that makes this information available pre-attentively, so that the user doesn't even have to think about it. This isn't always possible, but this is what we strive to do. So the point here is that any graph, okay, the more mundane name for a visualization would be a graph, right? Graph is a form of visualization. A map is a visualization. A map is a visualization of data, space, right? Graph would be some quantitative information. You saw a table there. That's also a visualization of numbers. Your timetable, for example, is a visualization of how your days and hours match. Okay, so there is a design that happens there, so that you can very quickly know that today is Wednesday, 2:30, and this is the venue, this is the class that I have. Right? So that's a visualization of information. So these are all formats that are available here of available. We know how to read those visualizations. But those are also visualizations. Visualization is not only something that is graphical, that is explicitly illustrated, a lot of illustrations. So even a simple table put together could be a good visualization. Okay, so this, when it is encoded, becomes this, and therefore it becomes easy to understand what it is. So this also, the same thing, can also be encoded differently. Okay. So instead of a dot graph, I'm using a line graph here, but then the relationship between x and y does not come through clearly as it did in the previous encoding, right? Now that is essentially the art and science of what kind of encoding to choose in order to communicate the point that you want to get across. Okay. So a lot of times, we probably end up with deciding to choose the graph, or the graph style that comes to our mind the first graph style that comes to your mind, right? So, okay, I'll do a bar chart for this one, I'll do a rank graph for this one, I'll do a parallel coordinate for this, and so on and so forth. without realizing that is this what my data is supposed to communicate. Okay? If your data is comparing something, if your data is finding out some kind of an outlier, you need to have different kinds of visualizations, or in other words, different kinds of encoding in order to communicate with us, right? So how do we know that you should be using a dot graph instead of a line graph? Okay, this is where a lot of my students have trouble. Okay, so I know that this is what I communicate, but I don't know how to encode them. Okay. So hopefully I'll tell you some things that will help you do that. So good visualization optimizes for the human visual system. This is where we learn a lot from perceptual psychology. This is a very old map, in fact, 1885, a very old visualization done by a guy called Marley. He was a trained locomotive engineer. Can you figure out, can you tell me what this is? If you can't read, for those of you at the back, that is Paris, this is Lyon, and these are the stations in between. I think it should give you an idea by now. Okay, and there on the top you see time of the day. It goes from 6 a.m. in the morning to 6 a.m. the next day. Okay, so it's a 24-hour clock, and these are the trains that go from Paris to Lyon, and it is in both directions. So you can see the beauty of the simplicity of this visualization. The entire timetable is compressed into one simple diagram. And then you can see, so you can read them even if you don't know, you've never come across a diagram like this. Okay, so this is now these kinds of diagrams or this kind of encoding now is called a Marley diagram. Okay, you can look it up. You'll find lots of very good and extensions of this. This is the original Marley diagram, but people have improved upon this and have created wonderful visualizations. So this, for example, is a train that starts at Paris at 6:30. The morning, and then it stops at the next station, and then there is a horizontal line there, right? So what does it mean? That's the duration of the stoppage. So it reaches at around. So every line is a 10-minute line, right? So it reaches at 8:20. It stops for about 5 minutes and then starts there. So every time there is a horizontal line, that indicates that that's the duration of the stop. If the line just cuts through, then it's a non-stopping train. The steeper the line is, the faster the train is. Okay, so there is a lot of meaning coming through with a very simple encoding. Okay, so this is an example of a great visualization. So this is the data, for example, you come across. So estimates of relative survival rates. You have this prostrate and then you have this variables, right? So percentage of survival and there is also a standard error that's kept here. And there is a lot of data and it's difficult to make sense of this, right? So this is a better encoding of same data. So you go for a scale from say 0 to 100. For example, prostate, that is essentially what you want to do, right, with the data are there. So if you look at prostate cancer, you want to know how does it taper off, okay? What does it remain, or does it increase? So you will notice that immediately there is a pattern that emerges, right? So as you get older, your chances of survival or the percentage of survival is becoming lesser, right? And that seems to be the case with all kinds of cancer. But there seems to be some cancer that's kind of uniform across whatever age group you are, but some kinds of cancer are not really very kind to older people than to younger people. So some cancer have very high success rate. When you get it young, you have a highly. So that is essentially the point that is happening. But none of that comes through here because it is just a table and it is not being encoded. There is an encoding that's happening here, but it's not the appropriate encoding. Okay? So this is again a version of a Marley diagram. This is the train train timetable between Surabaya and Yogyakarta, which are two stations in Indonesia. This is a Dutch map, so the language is in Dutch, and then later on improved by Japanese, when they occupied briefly during the Second World War. And compared to the previous, the original Marley diagram that I showed you earlier, this contains just a wealth of information. You can spend about an hour and a half on this single map, and then keep digging beautiful information out of this. This is being cited by Edward Tufte, who's considered to be a very important figure in the information visualization area. He's written 3 seminal books. So please look up Edward Tufte if you have not heard of him, and then look up his books also. He's written 3 wonderful books on visual display of quantitative information. So again, the same thing. The idea is the same, but it has additional information about the altitude of stations, as well as the type of platform these stations have. So unlike the previous timetable that I showed you, which is a passenger-facing timetable, this is a planning timetable for goods movement. So which is why these, especially for troop movement, troop-related goods movement. Okay? So this was used extensively during the Second World War, and Indonesia, as you know, is a bunch of islands, very poor road network, and it relies heavily on railway to transport most of the stuff. And during the Second World War, it was the only transportation that was available, and it was very critical for the army, the military to plan their ordnance movement, troop movement, goods movement, supplies movement, and so on and so forth. Okay? And all those altitude information and where which stations contain water sources and what are the kind of platforms that are available at various stations, so that the right kind of, say for example, if you're sending a tank to a particular place, you should know first of all whether the station can handle it or not, right? So all these things are. So I'm going to show very quickly some of the close-ups of these things. So this is a current day, the present day map of passenger train movement between the same 2 stations. So I just wanted to show you the contrast between how much we have lost in terms of the richness of information that is possible. I mean, it was so beautifully encoded in the previous version. This is currently what you see, because I just got curious to see what kind of timetables exist now, right? If I want to travel between these 2 stations, and this is all I got. And it took me a lot of time to figure out, and I've traveled in Indonesia, but yet I could not figure out what would be the best option that is available, because they are all dismembered. So all kinds of all trains, all types of trains are all placed separately. If it is starting from a particular station, then it is separated. So it's very difficult to make. It's not all information is available in one single place to make comparisons and so on. Okay. So this is, for example, the altitude information, distances, and this is all entirely handmade. These are the platform information I was talking about, right? How much is the height, and what kinds of amenities are available at the station and so on. This is the encoding that they have used to differentiate between the type of trains. Okay. So there is 3, 5 plus 8 type of stations, and then there is also, so there is 2 variables here. And you can see a very interesting encoding here. Okay, so this is all you need to know is this encoding, and then this encoding, when combined with some additional encoding, adds meaning to it, right? So the benefit of something like this is that once you know this, and then the square means something, then you will be able to put these things together. Okay, so it's kind of it's very learnable. Okay. So it's very easy. So the logic is obvious. Okay, so it's not some kind of a random encoding, right? So you will clearly understand what the designer is getting to, right? So this line, when squares happen, wherever squares happen, it is a seasonal train, right? Wherever circles happen, it is a irregular train. Wherever crosses happen, it is a special train, right? So there is one type of encoding to differentiate between the types of trains and then the speed of train. So when there's to interact, it reveals the categories very clearly. So how do the human visual and cognitive systems work? Fortunately for us, there has been some very good work. This book by Bill Cleveland is one of the seminal books in the area. summarizes the research into a coherent framework. I'm going to talk about that in the next 30 minutes or so. So it's called Elements of Graphing Data. These are all classics, so I don't know whether your library has one, but if it doesn't, I think you should get one. So Cleveland talks about three visual operations of pattern perception. Okay? So essentially, any kind of visual display of information. Okay? There are three things happening. Okay? So first, there is detection, which is the visual recognition of the geometric object that encodes the physical value. Okay. Second is assembly. It's the grouping of the detected elements. Okay. So individual elements can be detected. I can detect lines, circles, triangles, squares, shades, colors, etc. Right? And then when the assemblies and I'm putting them together. Right? Estimation is the visual assessment of the relative magnitude of two or more quantitative values that those assembled elements encode. Okay? So I'm going to go through each one of them. So detection basically happens through the eye. So this is a very nice engraving, very famous one. So, vision and knowledge has been, extremely entwined. Okay. So, vision has always been considered the noblest of the profession, dominance of vision over senses. In fact, over lunch I was, just talking about this to Leslie. So, from classical Greeks to the most modern Western thought, knowledge was regarded as analogous to clear vision, right? During the Renaissance, the five senses were the hierarchy of vision. Vision was always placed at the top. The visual senses were always at the top. It's been dominated. Some people call it the hegemony of the vision, right? Or determining everything, right? But things have changed since Descartes. So what he equated the vision with touch, which he considered to be more certain, less vulnerable to errors of vision. So this is one of the early guys who started questioning the dominance or the absolute certainty of what people. I mean, the Western science is based on observation, right? So vision always had this very strong prominence over other senses. You can see, entire astronomy was based on visual observation, isn't it? So, Friedrich Nietzsche criticized the treacherous and blind hostility towards the sense. These are all, I'm just pointing out the thoughts, key thoughts from these people, and I'm sure some of you will be interested in it. And the point of this slide is so that you will go and read more if you're interested, right? So I can't go into each one of them, but some of these people, philosophers and scientists, question the dominance of vision or question the knowledge that was derived purely from vision. Okay? Sartre was outspokenly hostile towards the sense of vision to the point of ocular phobia. Merleau-Ponty considered perception not only the sum but the simultaneous interaction of all the senses. I guess Kishore's work is going to be something like that, right? So it's a kind of a multi-sensory interaction. Knowledge is created not just by vision, but each sense influences the perception of the other senses as well, right? And it's a common example that I give time as students is that when you have a severe cold, you can't taste your food, right? Your food is wonderful, it might be, but it still doesn't taste as good. Heidegger, Foucault, Derrida have all considered the negative tendencies of sight dominance in the modern era. Michel de Certeau said, our society is characterized by the cancerous growth of vision, measuring everything by its ability to show or to be shown. So this painting by Caravaggio, I thought captures this doubt that Thomas had, because he just couldn't believe that Jesus came back alive, and only way he could make sure and confirm that he wanted to touch his wound, and then the touch was touch is what kind of confirmed it. Vision he didn't rely on. Artists have I don't know whether agree actually, but in order to even enjoy the other senses, it becomes necessary to suppress vision sometimes. Right? So there is this notion of how do we even begin to make knowledge of sense, meaning out of other senses. Maybe you need to suppress vision. I'm not sure about the 70%. Just over lunch. Leslie mentioned about 40%. So I got it from somewhere else. I guess we all have different sources. So 70% of body sensory receptors reside in our eyes. The eye is the visual cortex of the brain from the massively parallel processor. Okay, these are all guys from the visualization, visual design domain. So therefore, maybe our knowledge is not very accurate. It's important to understand how visual perception works in order to effectively. So, all said and done, we are just beginning to think about tangible and other sensory type of visualization, but essentially what we do is purely visual nature. But my hope is that we eventually will have other kinds of sensory perceptions which are used in visualization as well. But we just need to understand some differences. Like for example, it's not a camera, so dynamic ongoing construction project, attention is selective and filtering. Cameras have good optics, single focus, wide balance exposure, full image capture. Eyes are relatively poor optics, constantly scanning, constantly adjusting focus, constantly adapting. And it's a mental reconstruction of the image. So how the eye detects information, the visual system sees differences, not absolute values. Okay, so this will become very critical in the design of visualization. Okay? And it is attracted towards the edges. Okay? So the information resides in the edges and not in continuous surfaces. So, for example, an implication would be to maximize the contrast with the background if outlines of shapes are important. Visual system constructs surface color based on largely on edge contrast information. So a lot of times what we see as a particular color is not actually the color because it interacts with the environment, the background, the adjoining colors and so on. Okay, so we have to be very careful and understand colors and color interaction very well before we use them in our visualizations. We have higher contrast sensitivity in the luminance rather than the chrominance channel. Okay? So what that means is that so it is better to use grayscale rather than colors. Okay, if you want to show contrast and differentiation, especially if it is subtle differentiation. Okay, say for example, if you are creating a heat map of say all the constituencies in the country and creating like a geographical map of all constituencies, and then you want to show some data in it. Say for example the polling percentage. Okay, say you want to have the highest value of color to the constituency which has the highest polling percentage, say somewhere close to 80% or something, and a constituency which has the lowest polling percentage, say 30% or something. Okay, and then you want to show how it is distributed across the country. Okay, and then it is better to use grayscales because you have so many constituencies. Right? How many constituencies? We have 500 odd constituencies, right? Or 400 odd constituencies, parliamentary constituencies. Okay, so then the difference, sometimes the differences are going to be so minimum, right? So there will be constituencies like between say 50 and the next one is 51 or 51.5 and so on. Okay? And that kind of certain difference better comes across if it is in the luminance channel, right? The color luminance is basically shades of the same color. Okay? Chrominance is different color hues, right? Red, blue, green would be chrominance. Dark red, lighter red, lightest red would be the luminance, right? So our visual system corrects or often misreads, leading to misreading of information based on perceived visual properties. I'll show you some interesting experiments that illustrate this beautifully. Okay. So AGI detection, so this is a luminance, right? So our perception, we think of it, so the luminance value is this, right? Is less luminance, is more luminance here, right? But what we see is this. Okay? That is how I see it. Okay, it just sees records that change the value of luminance at the edge and then it goes back to reading it continuously. Okay, so what do you see? Which of these two rectangles is the darker gray? On the left? Are you sure? When changes are there? Okay. Any other take? Any other take? Yeah. Okay. You're closer. You're getting, but you're not. That's for the constant illusion. It's exactly the same gray value. So what was happening was, so the gray here and the gray here are exactly the same grays. There is a decrease in luminance, and here there is an increase in luminance. Okay, so what you see here is there is an increased gray and a decreased gray here. Okay, but so what we see, most of you thought of the entire left rectangle as being dark is because we see this as at a slightly lower luminance than this one. So this is the illusion that's called the constant illusion. It's also more, I think this is more popular one. Many of you would have come across this. Edward Edelson created this MIT article in 1995. So what's interesting here is that the A and B are the same value. Okay, even after, so I placed a patch of gray here, which is the same, and then it's supposed to. When I show it to people, people say, "No, this still looks like a gradient. It kind of looks like it's a gradient that is going there." So that's the correction that is trying. So what is it? What is the eye doing here? Can you tell me what is the eye doing here? Why are we thinking of this being lighter than this? Why they are exactly the same shade of gray? No, not only that. We are correcting for the shadow. Okay, we assume that because it is in the shadow, it is we are over-correcting. Our eye is over-correcting for it, and that's why. So again, it's now this is the thing about surrounded by this thing. So you see them as different color. You see them this gray as a lighter one, this one because it's just surrounded by exactly the opposite contrast colors, but they are exactly the same thing. Same thing happens in colors as well. They are exactly the same colors and so on. Okay, so I'm going to quickly go through a few other things that we learned from perceptual psychology. So we use, for example, what is called a semantically the same color set. So we use a lot of colors in visualization, whether it is like a simple paragraph like this or a more complex, maps and geo-visualization, so forth. Okay. So if you go to any kind of a default color assignment, this is how your software, for example, Excel will do it. It just gives you some random color assignment. Apple is blue, banana is green, blueberry is green, and so on and so forth. But then if you take a little bit of effort and then figure out, what would be the most appropriate color to use for these things, it just reduces that much amount of cognition. So remember the initial slide I was doing. So how do we pre-attentively help people to figure out what this information stands for, right? If they have to go here and then figure out the legend and then mentally map these colors and then it somehow it's clashing with your own knowledge of what colors these fruits actually carry, right? So you can imagine blueberry is not blue, right? It's some other color, right? So it's very disparate. So, so that's called the Stroop effect, the interference in the reaction time of the color. Reaction, not only is it not assigned color, but it also interferes with it. So it not only allows you to get to that pre-attentive processing stage, but it's actually deterring you from doing it, right? And that's the opposite. You're actually doing something to prevent people from even understanding their own sweet depth. Okay, so I'm going to ask one of you here. Can you read these? No, can you tell me the colors, not read the words? Any one of you? Yeah, just you tell me the colors, not read the words. Yeah, louder please. Anyone? Just read it. Yeah, go ahead. Okay. Now read the colors. Tell me the colors. One red, blue, one green. So it's probably going to take twice as much time. Okay, and you're going to probably make one or two mistakes along the way. Okay. So this brain's ability to recognize color of the words, since the brain reads words faster than it recognizes colors. Color recognition as opposed to reading a word requires more attention. Process, and there is an extensive response where is the brain already. So there is also things like pop-out, but colors are all showing very differently here in the projector. So if you want to, for example, highlight something, so you can see objects that are different color and shape rather than, so anything, not just color, if it is a different shape, if it is of a different texture, if it is moving as opposed to everything else stationary, so that attracts attention. So you might want to keep those kinds of things for information that you think is important or you want to draw attention. So these are more. The larger the chromatic difference between target symbols and other symbols, the easier to search for something. So there's a very, very contrasting colors. So here it's very small difference. And again, these colors are showing exactly the opposite of what it should. Okay? So the color, the projector is not calibrated. So for example, these are all reds and this is yellow. So yellow and red is very close to each other. At the color wheel, while yellow and blue are very far away from each other. So I probably will skip this one because another thing that we use is what is called the Weber's law, which is the just noticeable difference is proportional to the size of the initial stimuli. So have you all heard of Weber's law? So I'll just show it to you. So here the 10, so for example, the first one is a value that represents 10 kilos. The second one is a value that represents 20 kilos. You will be able to recognize it as clearly as two different sizes, and you will be even able to estimate it very accurately. Right? So if they take this number out and ask you how much bigger the bigger square is as compared to the smaller square, most of you probably get it as probably close to twice the size, right? Suppose I give you this 100 and 110, it becomes much harder. Do you agree? So that's essentially based there. So in terms of how it translates, we judge based on relative, not absolute differences. Weber's law is why grid lines are useful. So, for example, this is a scatter plot of, say, some cars that are showing, so it's miles per gallon, how much car gives in terms of miles per gallon mileage, and how much it weighs. Okay?
So these are all different makes of cars, going from Japanese car out there to American cars somewhere here. Okay? But there's a lot of dots there, and then you can play around with the visual design of it to make sure that you are able to make better sense of it. So maybe smaller dots makes it immediately better because all the overlaps are reduced here. Some kind of grid line helps place them because you are now better able to track them. So here, it is, for example, here it's very difficult to see whether it is midway between 15 and 20, or is it much closer to 20 or 25 and so on. Right? So like, you can even distinguish the type of grid line. So fives are all multiples of fives are different from the multiples of 10. So it eases that much. So if I were, the classic design process for a bar chart would be something like this. You start off with something like this, and you think about whether you need those very complex grid of vertical and horizontal lines. Sure, they help, but does it conflict with the diagrams themselves? Is it making it too cluttered? Or is it too much of noise? Okay, so how about this? Maybe background is not very relevant, so it gives me better contrast now. Then I don't need the top and the right lines at all. I remove that as well. But still, the horizontal becomes very difficult to read, especially if it is further removed from the y-axis. So this improves it further. I have this very clear red line that goes. So this would be actually what I would end up with, where it's much more cleaner. You're just comparing the heights here, and there is guidelines for you to help you to compare. Okay. All this. So Edward Tufte, in one of his books, actually talks about this case study of the NASA Challenger space shuttle disaster that happened in '86, I think. I'm very sure, I'm not sure about the year. It went up with 8 astronauts. One of them was a school teacher, and then it crashed before, like 50-60 seconds in after launch, it crashed. And there was a inquiry commission that was constituted to figure out what went wrong. And then they found out that it was a very simple communication problem. Okay? So there was two parties that were involved. One was NASA, which was the space administration, which was responsible and the public-facing organization that was responsible for this Challenger launch. And then there is this rocket guys, Theopol Martin, which is a private company which supplies the rocket. The rocket is what puts the Challenger shuttle in the orbit, right? So it turns out that the Theopol Martin guys, the rocket people, actually had enough data to tell NASA that, in fact, they told NASA that it's actually not a good time to launch the shuttle, because I'll show you the data. So just very badly communicated. Okay? And Edward Tufte went through the entire report and found out the systemic problems in communication, the very poor diagrams and communication charts that they use, and then went about redesigning and then said, now if I'm going to communicate this idea to NASA to tell them to abort the mission, this one simple diagram that I need that would have communicated everything that I wanted to know. Okay? So these are actual communication that Theopol Martin sent to NASA, arguing that the mission should not go ahead as planned. Okay, and they laid out all this reasoning in the scientific data to support why they are recommending a no launch. Okay, so it goes on for 13 pages or something like that. Goes on like that, and this is what Edward Tufte eventually did. Okay, so he basically crunched all the information that was available in this entire report or entire communication, 30 pages of communication, into one single diagram, which he claimed that would have communicated clear as a day to NASA that this is a mission this is a disaster waiting to happen. Okay. I'll explain to you what these are. These are temperatures. So, like as you might know, like in any launch, especially very high stakes launch like this, with 8 astronauts are being sent. They launch several test missions and collect data about weather patterns, what is the kind of damage that happens to various parts of the rocket, Challenger. And these are all dummy missions without any live astronauts present. And they collect data and then they kind of titrate their mission and the parameters and so on until they perfect it. And when they're confident that they have everything under control, they send that to people, right? So that is the process. So NASA, these are all test launches, and these are all temperatures on the day of these test launches, and this is the damages to the O-rings. O-rings is eventually what was found to be the cause of the crash.
O-rings are this the washer kind of things that exist between different stages of a rocket. Okay, so they tended to fail at low temperatures. Okay, that is the data that's what. So the more damages seem to be occurring at lower temperatures. Okay, and the scheduled launch of this particular mission was on a particular day where the forecasted temperature was going to be in the 26 to 29 degree Fahrenheit. Okay, so this was a clear no-go, right? So first of all, they didn't have any data at all
for such a low temperature launch. Second of all,
it is very clear that the lower the temperature, the more damage it seems to be having, so it's better not to launch it on. Wait for a day where the temperature is here, somewhere around here, 70, 75, much safer to launch. Okay, but they did a very poor job communicating it, and therefore they went ahead because NASA was looking at it as like a major political and a PR thing. Reagan was the president at the time, and he had a lot going for. His administration was behind. Launching it on that day because they had kind of built up the entire nation towards this whole thing, right? So, again, simple problems of detection. I'll quickly go through assembly. Estimation I'm going to skip because it is purely analytical in nature. So, Gestalt psychology, you heard of Gestalt? Okay. So, there are two things that we, use heavily. Okay, so Gestalt psychology, if you don't know, they are based on the works of these German psychologists. They call them the law of pithiness of goodness. Things are organized spontaneously, assumed to be in the simplest configuration. Perception as organized in structured wholes rather than some of their constituent parts. So they talk about this emergent, holistic, independent, and in context. Everything makes meaning, in context, and it's all emerging nature. Okay. So they came up with a set of laws. Okay, so these are mostly like heuristics, and depending on which source you consult, there are 3 laws, 5 laws, 8 laws, and I got about 10 laws. Very quickly, I'm going to go through. So can you make out the picture here? What do you see here? Yeah, you see a dog there. You see a Dalmatian sniffing on the ground. Okay, for those of you seeing this for the first time, you don't see it at all in the beginning, but once you see it, you cannot not see it. Right? You cannot unsee this at all, right? And it kind of remains. So this is an amazing ability of our eyes to be able to glue together these random splotches and then create this non-existent dog out of nowhere, right? And then, so that is, the mind sees the whole, then the parts, and often sees more than what specifically stated by individual parts. So this is a good example of a logo design done by a graphic designer that exploits that emergent property, right? If these 4 cones are not there, what you probably will see is a circle, right? A 2-dimensional flat circle. The moment you see this, very strategically placed like that, you're seeing a sphere, right? The sphere doesn't exist there, okay? But our mind sees it. So this is a logo for a hotel. You see a bed there. People see curves of the bed and the softness of the bed and everything, but nothing. It's just a blank space there. It's just a position of a black line and inverted E there. Okay, the second one is invariance. The mind recognizes simple objects independent of rotation, translation, scale, deformation, etc. Right? No matter in what orientation, scale, size it exists, we will recognize this. Proximity, elements that are close together are perceived to be related than elements. So this is a very equidistant organization of these dots. The moment I insert some kind of a gap, we see them as two columns. Here we see them as two rows, right? Then two rows, two groups of things, right? Elements that are close together are perceived to be related than elements that are farther apart. Okay, so you see very clearly battle lines drawn here, one group of people, another group of people. There are also other Gestalt principles that this painting very cleverly emphasizes. There is also similarity of kind of warriors, so you know that this one kind. There is also a common fate, a law of common fate that we will talk about a little bit later on, where one group is looking at one direction, the other group is looking at another. So these artists have, historically exploited Gestalt, through trial and error, or their genius, quite unconsciously for ages. Okay, but when we look at these kinds of things, we understand why does it work. Okay, now we are able to explain art in terms of Gestalt art. Why is that it appeals to us? Similarity I talked about, enclosure, elements that are enclosed by anything are perceived as belonging together. Okay. So those of you familiar with Breaking Bad will know its iconic title sequence. Continuity, we use this all the time whenever we have trend charts, right? We use this continuity principle a lot. Closure perceives a set of individual elements, single recognizable pattern. Mind perceives objects as symmetrical shapes to form around the center. We see a set of three symbols rather than, say, for example, we don't see this as one set. This is a separate set, right? So symmetry plays a major role in the way we organize this information on the screen. Figure and ground, we either perceive figures or ground. So for example, if I'm standing here, I am the figure and then this is the background, right? Figure and ground, whenever that distinction or the clarity doesn't exist or it is ambiguous, we get very confused, okay? So in visualizing, we try to avoid that problem, right? Connected elements are perceived as together. Okay, for example, a bunch of data here. Okay, so how it gets progressively better by for example, using similarity and then by connection later on. So this is also a visualization of a network diagram. Common fate is what I said, right? The elements that share the common fate, like moving in the same direction as belonging together. So this is I'm going to show you some art pieces, artwork, right? Paintings, photographs, mostly photographs, and I'm going to ask you which Gestalt is at work here. Okay, what do you think? Similarity, okay. Emergence, okay, dress emerges from nowhere, right? Or it could be a closure also. Okay, we have a problem with this signage, right? Which side is Lima? Is it left or up? Okay, so what is the problem here? Which Gestalt law is not applied here? Proximity, right? So we are not able to, because there is equally proximate, right? These arrows could be to Lima, both arrows could be attributed to Lima, right? So a better design would be to make this proximity not so ambiguous, right? Put these arrows and the text together, so you very clearly you can see that it is. Continuity. Common fate. Similarity. The famous photograph. Common fate again. Similarity, common fate. Yeah. Figure and ground. So this photograph is an interesting photograph only because the smoke seems to be going pointing to the same direction that the Mao is pointing to. Okay, if Mao is pointing to the opposite direction, this photograph loses all its interest. Okay, so continuity, so this, so this data, we clearly see some pattern emerging. So same data now we use similarity. So this is the data I was showing you. Miles per gallon weight in this thing. We add another variable to this. How many number of cylinders that the car has? 4, 6, and so immediately there is some meaning that's coming, right? The higher the number of cylinders are there, the less fuel efficient a car is, and they're very clearly grouped, right? So you have more fuel efficient cars which are less number of cylinders. The heavier the car is also. So there is a kind of a correlation between heaviness of a car, weight of the car, number of cylinders, and fuel efficiency. Very clear. Okay, say for example that this is there. Using differences to colors, you can also show it by symbol, by shapes. Suppose you don't have the color channel available to you, it has to be produced in black and white. Again, you have problems like this. You can improve it by using only outlines. You can also directly encode the number itself as a symbol, but when it overlaps with each other, then it causes some problem with the numbering system. So things like this. The continuity use to show the trend. So again, the angle of the slope tells you a story, right? Okay, so some of the encoding semantics that the Gestalt brings out for us is these things. Okay, so we use things all the time, like shapes that are connected by contour. Thickness of the connecting contour also can mean something. Okay, a thinner connection means less, or less tenuous connection. A thicker line means a stronger connection, right? So they all have meanings now, right? So you can pack so much of meaning in the encoding that you use. We saw enclosures like this, even the types of contours, types of relationship, right? So you want to show different types of relationships. Say, for example, family members different from friends, right? So thickness would not, be relevant there. You have to show different types of lines. Okay. So this again, is something that I want you to. I won't have the time to go through it, but you're familiar with V.S. Ramachandran's work. These 2 books are something very good. He talks about these 5 principles, which is where I wanted to stop, but probably won't have the time. Okay, so big shape. It talks about these principles, which we again use a lot in our visualizations. So let me quickly conclude my. Yeah, so I'll just, okay. So I'll just, so what I'll do is, I have a section called talks and workshops. So I'll probably put up my presentation slides, there. So if any of you want to take a look at it and then look at the rest of the slides and the references that I mentioned here, so that would be a good place to go check it out. I just wanted to show you this last slide so that you can take a picture or note it down. Thank you.